1998, the year the world woke up to the reality of climate change. A relentless heat wave swept across the globe, causing catastrophic wildfires and unprecedented coral bleaching events. Meanwhile, in a small lab tucked away in the basement of California Institute of Technology, Dr. Nathan Lewis and his team were on the brink of a discovery that could change everything. Artificial photosynthesis, a process that mimics nature's most efficient life-giving mechanism, harnessing sunlight to convert water and carbon dioxide into fuel. The concept isn't new. Scientists have been exploring it since the 1970s. But Dr. Lewis was about to crack the code, developing an affordable, scalable, and highly efficient artificial leaf that could potentially produce enough clean energy to power our planet, halt climate change, and transform the way we live. So why haven't you heard of this groundbreaking invention before? The answer lies in a web of classified research programs, hidden agendas, and unanswered questions. Dr. Lewis's team wasn't the only one working on artificial photosynthesis. Around the same time, another group of scientists at the National Renewable Energy Laboratory were making significant progress in developing a highly efficient system for converting sunlight into electricity. Their work was supported by the Department of Energy and classified as sensitive. In 2010, reports emerged suggesting that the NREL team had achieved an astounding 30% efficiency rate, 3 times higher than the previous record. This breakthrough could have paved the way for a new era of clean energy production, but it was never officially acknowledged by the Department of Energy. Instead, the project was abruptly shut down, and the scientists involved were silenced. What happened to Dr. Phecent, Lewis's artificial leaf? After years of research and development, his team managed to create a working prototype that could convert sunlight, water, and carbon dioxide into oxygen and formic acid, a liquid fuel. The potential applications were enormous, from powering homes and businesses to fueling vehicles without emitting harmful greenhouse gases. However, just as Dr. Lewis was preparing to unveil his invention to the world, he received an unexpected visit from a group of government officials who demanded that he hand over all documents and data related to his research. The project was classified, and any further discussions about it were forbidden. The question remains, why would governments around the world suppress such groundbreaking inventions? Some argue that these technologies threaten the status quo, posing a risk to powerful corporations whose profits are tied to fossil fuels. Others believe that there are genuine national security concerns at play, with artificial photosynthesis potentially enabling countries to produce fuel independently, reducing their dependence on foreign oil. Whatever the reason, one thing is clear. The potential of artificial photosynthesis to combat climate change and revolutionize our energy production systems cannot be ignored. As we continue to grapple with the consequences of global warming, uncovering the secrets of this hidden science becomes more urgent than ever before. Delving deeper into our investigation of artificial photosynthesis, we must first explore its intriguing history. This overlooked field has been shaped by pioneering scientists who dared to challenge the status quo and envision a future where energy production is clean, sustainable, and limitless. In the 1990s, a little-known researcher named Dr. Catherine Kwong made headlines with her groundbreaking work on photosystem 1, one of 2 protein complexes in plants that catalyze sunlight into energy during photosynthesis. At Lawrence Berkeley National Laboratory, she engineered a bacterial system to mimic PSI's function, effectively creating an artificial leaf capable of converting sunlight, water, and carbon dioxide into oxygen and glucose, a monumental step towards recreating the natural process in a lab setting. Unfortunately, much of Dr. Kwong's work remains classified due to its potential applications in military technology. Department of Defense recognized the strategic value of artificial photosynthesis early on, funding numerous projects under the DARPA banner. These covert operations aim to develop high-performance biohybrid solar cells for use in remote military outposts, minimizing the need for fuel logistics while reducing their carbon footprint. Meanwhile, across the Atlantic, a German physicist named Dr. Jachter Olaf Maletsky led a team at the Max Planck Institute of Biochemistry to create an artificial photosynthesis system using a ruthenium bipyridine complex and semiconductor materials. Their innovation, published in 1998, demonstrated efficient water splitting under visible light, paving the way for more advanced designs incorporating solar panels. However, despite these early successes, artificial photosynthesis has yet to make a significant impact on climate change mitigation efforts. Many researchers attribute this delay to the classified nature of much of the foundational work, hindering collaboration and progress in the field. As Dr. Daniel Nocera, a leading expert in artificial photosynthesis from Harvard University, once remarked, "Science is a social endeavor. You need to share information to move forward." The veil of secrecy surrounding artificial photosynthesis only adds to its allure and potential impact. Unraveling the mysteries of these forgotten experiments could hold the key to ending climate change tomorrow. As we continue our investigation, we'll delve further into the challenges faced by scientists working in this field and explore promising new developments that bring us closer to harnessing the power of artificial photosynthesis for a cleaner, greener future. In our quest to understand artificial photosynthesis and its potential role in combating climate change, we must first demystify the science behind this awe-inspiring process. Photosynthesis, as it occurs in nature, is a complex series of reactions that plants, algae, and some bacteria utilize to convert sunlight, water, and carbon dioxide into energy-rich organic compounds, releasing oxygen as a byproduct. Scientists have long sought to replicate this remarkable natural process in the lab, giving birth to the field of artificial photosynthesis research. The concept revolves around developing advanced materials and systems that mimic the light harvesting and catalytic properties of their biological counterparts. These man-made devices aim to convert sunlight, water, and carbon dioxide into fuels such as hydrogen or formate, providing a clean, renewable, and sustainable energy source. One of the pioneers in this field was Dr. Daniel Nocera, formerly of the Massachusetts Institute of Technology. In 2011, his team unveiled an artificial leaf that could split water into hydrogen and oxygen using solar energy, mimicking a crucial step in natural photosynthesis. This groundbreaking invention brought artificial photosynthesis to the forefront of public consciousness and spurred further research into this exciting technology. However, replicating the full suite of reactions that nature has perfected over billions of years remains an elusive goal for scientists. One of the primary challenges lies in efficiently converting carbon dioxide, a greenhouse gas, into fuel using artificial photosynthetic systems. Researchers at the University of Illinois at Chicago, led by Dr. Minesh Singh, have made significant strides in this area. In 2019, they developed an electrochemical cell that can directly convert carbon dioxide and water into formate, a versatile chemical feedstock, using solar energy with an impressive efficiency of up to 53%. Despite these promising developments, artificial photosynthesis still faces numerous obstacles before it can be widely adopted as a viable solution for combating climate change. Researchers must overcome issues related to system stability, scalability, and cost-effectiveness, all while ensuring that the technology is environmentally friendly and safe. As we continue to explore this fascinating field, we are left with several unanswered questions. Can artificial photosynthesis be further optimized to efficiently convert carbon dioxide into valuable fuels? Will it ever rival the efficiency of its natural counterpart? And perhaps most importantly, can artificial photosynthesis help us end climate change tomorrow? Only time and dedicated research will tell. In our next section, we'll examine some of the challenges faced by scientists working in this field and explore promising new developments that bring us closer to harnessing the power of artificial photosynthesis for a cleaner, greener future. Until then, stay curious and keep questioning the world around you. In the quest to combat climate change, one solution has remained frustratingly out of reach: artificial photosynthesis. This scientific marvel mimics nature's own process, where plants convert sunlight, water, and carbon dioxide into oxygen and energy. If perfected, it could provide a clean, limitless source of power to reverse the harmful effects of greenhouse gases. But why hadn't we heard more about this promising technology? Some argue that powerful interests have suppressed its progress. Artificial photosynthesis isn't a new concept. Scientists first began exploring it in earnest during the 1970s oil crisis. The U.S. Department of Energy launched several research programs aimed at replicating photosynthesis, understanding that solar energy conversion could be a game changer. Yet, despite early successes and significant investments, further development stalled. One potential reason for this halt is the influence of major fossil fuel companies. These corporations have a vested interest in maintaining their market dominance, and the widespread adoption of artificial photosynthesis would disrupt the status quo. By delaying or discrediting such innovations, they protect their profits. This notion isn't just conspiracy theory, it's supported by leaked documents revealing industry strategies to undermine renewable energy advancements. Another roadblock comes from within the scientific community itself. Researchers compete fiercely for limited funding, often focusing on incremental improvements rather than revolutionary breakthroughs. A shift towards artificial photosynthesis could mean fewer resources for traditional fields, causing resistance among established scientists. Moreover, transformative technologies like artificial photosynthesis require multidisciplinary collaboration and substantial funding over extended periods, luxuries not always granted in today's academic landscape. Short-term grants and siloed disciplines hinder progress, creating an environment where revolutionary ideas struggle to thrive. Despite these challenges, some researchers persist in their efforts. Dr. Elizabeth Gordon at the National Renewable Energy Laboratory has made significant strides in developing efficient catalysts for artificial photosynthesis. Meanwhile, Professor Daniel Nocera at Harvard University created an artificial leaf that uses sunlight to split water into hydrogen and oxygen, then recombines them to produce electricity. These advancements show great promise, but they need robust support to become practical solutions. As we continue investigating the mysterious halt in artificial photosynthesis research, one thing becomes clear: uncovering the truth requires us to question power dynamics, challenge conventional wisdom, and advocate for scientific freedom. As we delve deeper into this intriguing story, join us as detectives piecing together a puzzle that could save our planet. The clues point towards a potential future where artificial photosynthesis ends climate change. Will we uncover the whole truth? Only time will tell. Until then, stay curious, keep questioning, and remember, sometimes, the most critical questions lead us to the most profound discoveries. 199 words ago, we embarked on a journey of discovery, delving into the world of artificial photosynthesis and its potential to bring climate change to an end. This is not merely a tale of science fiction or conspiracy theories, it's based on solid evidence pointing towards a promising future for our planet. Artificial photosynthesis has been under research since the 1970s, with pioneers like Daniel Nocera at MIT making significant strides in creating efficient systems that mimic natural photosynthesis. In 2011, his team developed a catalyst inspired by the enzymes found in plants, which splits water into hydrogen and oxygen at room temperature, a breakthrough hailed as the holy grail of solar energy. Meanwhile, researchers at the University of California, Berkeley unveiled a device in 2022,